the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you to episode 32, where today we're going to be talking about simulation theory.
That's right, simulation theory.
Cool.
Before we get into the episode today, we hit 1,000 followers on Spotify. So shout out to everybody that followed us on Spotify. We did call it, by the way. Last episode, I said we were going to hit it before this episode.
And we hit it on the day.
We did.
We hit it on the day. It's actually because we were going to have, we were actually going to do it yesterday. But then I think we had one day, which was unsatisfactory. And then it went back up. Or something like that. Anyways.
No, it was fine. Yesterday was fine. Anyways.
Also, something really interesting, since we are just talking about our podcast, just our history and stuff. One very interesting thing that I was noticing, that Parker and I noticed today, is that our subscriber or our follower growth is insane. So thank you to everyone. For example, in the first 6 months of this podcast, which was from May to September, we had 500 followers on Spotify. And as you know, in 1 month, which is today, we've reached 1,000 followers on Spotify. So I think that is awesome. So thank you to everyone who is continuing to follow, continuing to subscribe to us. Really means a lot. Really does.
And also, if you follow us on Instagram, math.physics.podcast, we post every time like something happens, something cool happens. And August 20th, we posted 200 followers on Spotify. 1 month later, we posted 500. And 1 month later, we posted 1,000.
Oh,
so that's awesome.
God damn.
Thank you to everybody that's been following on Spotify. But technically, total followers, we hit 1,000 a while ago. Because on YouTube, we have 40.
Podbean, yeah.
On Podbean, we're at like 175. So
can we measure Apple Podbean followers?
No. You mean Apple Podcast, but no.
I mean, sorry. Apple Podcast followers.
Yeah. No, we can't because they have really bad analytics. But, yeah, that's it, I guess. We will get started into this episode. So life as a simulation. So we're going to talk about half like physical concepts, half philosophical ideas. So yeah, to get this episode started, we're going to talk about creating consciousness. It's one of the hints that lead us to thinking that life is actually a simulation. So we have computers on Earth right now that can not very well. They can't do it well, but they can somewhat simulate brain activity. And so
not very well. Not very well right now. We do not have enough power to even fully understand the brain yet.
Yeah. People speculate that with the exponential growth of technology, that eventually we will have a computer that is as powerful, if not more powerful, than a human brain, and that can simulate a person.
And that is actually, sorry.
Yeah, go ahead.
Interesting fact, I just want to cut in. That's known as the technological singularity, the moment in technology where we can make something sufficient enough to replicate the human brain. So basically, like, AI, what everyone talks about, the perfect AI machine that hasn't been made yet, even though there are multiple AIs, but the perfect AI machine will be able to perfectly, basically, simulate a human conscious brain. It will be.
I actually thought the singularity was when technology can just teach itself at an exponential rate, and then it just knows everything. Like the point
AI,
where it knows
like singularity is kind of like a nice borderline to put it at, because when technology reaches the level as us, we can say that singularity has been reached. And the moment it gets better than us, it breaches that singularity or something or whatever.
So the reason why this ties into simulation theory is because if us humans can program, using the laws of physics we were given, we can program a machine that is basically an artificial human. What tells us that we are not artificial humans? That our brains were coded by something, right? The creator of our simulation. Our brains are just coded machines that aren't real. They're just brains. And if, let's say, this computer that we create in the future can experience like emotions and independent thoughts and all these things that we see in human brains that we think are unique to us because we are, we think we're special because we're so smart and we have big brains. But what if it's not special? Like every creation, whether it be technological or biological, that has our brain capacity and brain, what am I trying to say? Brain effectiveness, something like that.
Okay.
Yeah, like what tells you that we are not just programmed things of atoms, Yeah.
So a really good TV show, if anyone actually watches, Westworld, is a fantastic TV show that literally is talking about everything that Parker just stated. Like everything that he said is basically the plot of Westworld, where it's like these conscious robots kind of thing. I mean, I don't want to get into the TV show, but basically the idea is if we can code something to be artificially intelligent, what tells us that we are not the same beings that we just created? Right? There's nothing that can differentiate us from them at that point. If we can make them, perfectly biological and stuff like that in the future, there's nothing that will be able to differentiate, at least mentally speaking, like, for the mind, not really the body, but mentally speaking, there's nothing that differentiates this AI from then us. So that poses not only a philosophical question, but also a who's whom question.
Correction, whom is never actually correct. That's from The Office.
Yes.
Our next point is quantum mechanics. You know how much we love to talk about quantum mechanics, but let's all conjure up the double slit experiment in our brains. And if you guys aren't familiar, I will briefly explain it. So it's when you have two slits, and then you shine a light at the two slits, and then you have a screen behind the two slits. And then what you see is, instead of having two bars of light, which is what you would expect, right? Mm-hmm. You have this interference pattern. So it's like these light spots and dark spots. And so if you do the math behind it, what happens is that the two waves, because you separate it into two slits, right? So the two waves that emerge from those slits interfere with themselves and then create constructive and destructive interference. And so that is essentially one of like the conceptual highlights of quantum mechanics. Mm-hmm. What this indicates in terms of simulation theory is that nothing that is being observed in the universe is rendered, quote unquote, right? So if we're not observing something, the universe doesn't actually like put it into the physical reality, right? Mm-hmm. And so in terms of the double slit experiment, if we don't know which slit the photon goes through, then that information isn't encoded into our reality. So it has, right, all these options. Mm-hmm. This is hard to explain without visuals. But it can be in either one of the light spots, and it shows up essentially randomly, but not randomly, because some spots are forbidden than others.
Yeah.
So all that to say is that some elements of reality just aren't really manifested until you look at them, and that kind of is analogous to video games, right?
Observe or like measure is a better word, not really look.
I guess, yeah.
Yeah.
Like measured, like that's like if you know anything about like video game designing.
Yeah, I was actually just gonna give that analogy. I was actually just gonna say that. Yeah.
So if you're playing like a first-person video game, and whatever you see on your screen is being rendered, right? Like every pixel on your screen is passing through your CPU and being thrown onto your GPU, whatever, and being thrown onto your screen. But you're not actually in a 3D space. Everything that's behind you is not actually existing while you're not looking at it. You know, of course, this depends. This is, you know, not 100% accurate because I'm not a game designer, but it's a good analogy. Some games work like this, right?
The way the games work is basically because they want to reduce your GPU and CPU load onto your desktop instead of rendering the entire environment. As you turn your mouse, like as you turn your cursor and as you turn your first person view, the CPU and you're basically the game is rendering it as you see. And whatever is out of your field of view is now being deleted from basically the storage that is being, rendered. And so there's a specific amount of storage that's being rendered. And the only thing that's being rendered is what is your field of view. Everything around it, everything beside it is different. Now, like there are new technologies like RTX and stuff that we can go into maybe later. But yeah, that does it a little differently. But
also I wanted to say that
game mechanics.
Like the inside of, like, for example, if there's a building in a video game, right? The inside of the building is just going to be like completely empty. There's just nothing inside. Yeah. It's just a wall that looks like a building. Or for example, if you have a rock, it's not actually a solid rock. It's just something that has the shape of a rock. But if you like clip into the inside of the rock, you'll see it's just some empty thing. All that to say is that the ideas that stem from quantum mechanics and some of the conceptual experiments that we've covered in class / discussed on the podcast kind of indicate that the universe works the same way as a video game, right?
With like every personal, like every one of us is like an individual first person view. Yeah. Kind of like some person in a higher dimension is basically playing us and we have no idea. No, that's like a joke, but like, yeah.
I mean, who really knows?
I mean, to be honest, like that's the thing, right? I mean, the whole argument I think just stems from the consciousness argument, because like everything depends on like how we can even define it, right? Because if in fact we do come to a stage, I mean, we just said this, but if we can create consciousness, how do we know we aren't that creation? Like that itself is like the major philosophical argument for this entire simulation theory.
One thing that I always love to visualize is that our observable universe is like a globe, you know, like how some of us have globes just sitting on our desks or whatever. Our entire universe, or our observable universe, is just a globe that's sitting on an alien's desk, right? like he just copped our universe, and we're just sitting on his thing. And whenever he's bored, he looks at it and he's like, "Oh, look at Earth. There's just people walking around on it. All right."
No, but he's gonna see the whole universe. I do not think he'll be able to see Earth.
Well, he can zoom in on whatever he wants, right?
Oh, but that's a pretty high-tech globe.
I know. Well, he's an alien that has a universe as a globe, so of course I'm assuming he's pretty high tech.
Yeah, that would be pretty crazy though. That would be pretty crazy.
This alien is like some crazy like coder. He's like in grade 6 taking a coding class, and like as a project he just coded a universe
casually.
And it's not even that big of a deal because, you know, it's just part of his curriculum.
Part of his curriculum to code a universe.
All of his buddies.
All people must code universes.
Yeah, all of his and like, you know, he chose, right? He programmed into his own project the laws of physics that we know today. Of course, other students in that alien class are going to have different universes that have different laws of physics, different whatever. And it turns out that the quantum mechanics that we see here on Earth is just ways to save on like load for his GPU, right? He's like, if no one's looking at this photon, why do I have to Why do I have to program it into reality?
Make it do some certain thing. It can just do anything I want it to.
If no one actually knows which slit it goes through, let's just say it goes through both. Whatever. It'll make it a lot easier on my computer and whatever. So
well, I mean, yeah, there's obviously a lot of jokes in science fiction and a lot of. I mean, we technically, we don't really know, but that's all just thoughts.
I mean, I think if we knew that was true, everyone would know. Everyone would also know that is true.
Yeah, for sure. Mm-hmm. Okay, continuing on the podcast now.
Next up, we want to talk about Fermi's paradox.
Next up, Fermi's paradox. Yeah, so I think we covered Fermi's paradox in another video. If we haven't, or if you haven't seen it, Fermi's paradox is basically a long way of saying, hey, how are we the only people in the universe? How are there not other people in the universe? How have we not, in the billions of our years of our existence, never found any other civilization, any other planet that's habitable? That's basically the idea of it.
Yeah, there are easy ways to explain this, and just that things are very far away.
Yeah.
And maybe, the technology on both sides, like, if there was a potential alien out there, maybe their technology isn't as good as ours, so they wouldn't be able to receive any signals or send any signals, but they're still there.
Because always remember, like, to that technological alien argument, there's always the other side too. Like, we don't necessarily have to go there. The alien can also come to us. Like, we're not in a big rush. But at the end of the day, like, what would we do if an alien spacecraft just came to our planet? Because, to be honest, we have lived, 5 billion years? I mean, or at least the Earth has. Or at least, let's say human civilization has lived, like, even 100,000, 200,000 years, let's say. It's still never seen any sight of any kind of contact.
That is all speculative.
Recorded. Sorry. Recorded.
Bob Lazar on YouTube, Joe Rogan podcast.
Okay. Yes.
If you are interested in aliens and things like that, Bob Lazar is a physicist that worked at Area 51. I forget the name, but it's not actually Area 51, but it's like a lab. It's a lab off of in the same location.
That podcast is one podcast that
crazy.
Literally, no, it didn't literally, but it blew my mind.
Yeah.
It was like, it's so insane. Bob Lazar and Joe Rogan. It's one of the two. Which one is it? Because he has two,
right?
What
do you mean?
Or does he only have one pod?
No, I think it's one.
It's just one, right? Okay, whatever. But that is a must watch. Like, it is so good. I can't even explain it. Explain it.
The reason why I believe him is because this guy is an MIT doctorate degree, whatever, crazy physicist that, he has no reason to lie. He has nothing to gain from releasing the information that he has. And
he actually lost a lot of
he lost a lot
because of the information he released.
Yeah.
Yeah, and I don't mean all of that's on the podcast, but
let's talk about simulation theory again.
Yeah, let's talk a little bit about this podcast, not about Joe Rogan.
So Fermi's paradox, why does this indicate that life as we know it is a simulation? Well, let's suppose that humans are the only life form in the entire universe, which is so incredibly improbable.
Mm-hmm.
But let's assume, what does that really tell you about reality itself? Right? Out of all of the possible initial conditions of the universe, there's only one tiny little speck of dust that can host life. It kind of leads you to think that we're just kind of an experiment that was just put here. What happens if we let particles move around on their own, what'll happen? And then obviously now we're here and we've got computers and microphones,
and we're pretty much destroying the Earth too right now. So if we are in fact the only planet in the universe, we're destroying that one. So
we're not doing a very good job.
Yeah, we're not doing a very good job of keeping it,
Yeah,
good.
I am an optimist, though. I do think that the environmental crisis will work itself out. No, I'm not saying that if we continue how we're living right now that it'll work out, but I think that people are smart enough to eventually come around to the fact.
I don't know about that. In the day and age we live in, like, I don't know if people are smart enough to come around to that. Like, I definitely believe that there are a lot of people that even right now are still smart enough to know what's right, but there's really nothing that you can do with all of these, crazy factories just killing the environment. All across the world. It's not one person's problem, it's the whole world's problem.
So yeah.
Anyways,
the
deterred from the topic once again. Sorry.
The idea is that we are all every living thing. We're not even talking about humans that can invent things. We're talking about microbes and viruses and panthers and whatever. Everything that can be alive can only be found on Earth. That is just a crazy, absurd idea that could only be true if this massive infinite universe thing is encoded or created or simulated.
Yeah,
perhaps.
because technically, again, that's the entire thing, right? But there is a scientific version of it in the fact that the universe is just far too big for us to explore it yet. But but then you can also be like, well, if we haven't explored it and we haven't seen anything yet, so it's safe to assume that we could still be in a simulation. Well, until we see something, we can't really rule out the simulation argument, or at least in this context, in the Fermi paradox context.
Yeah, I think best case scenario, like we're traveling somewhere in space, we meet an alien species, and then they give us some like equation, and they're like, because they're way more advanced than we are.
Equation. What?
No, they're way more advanced.
They're not going to come to us and give us an equation.
Listen to what I'm saying. They're going to be way more advanced than we are, so they don't really care about us. They're like, whatever. Like they're just a bunch of monkeys chilling in space. So they'll give us an equation, and we'll be like, oh shit, like this is some crazy like next level equation, and then we'll become like slightly more powerful due to the thing that knowledge.
I highly doubt if they do come, they're gonna come and hand us a piece of paper with an equation.
I mean, one can dream.
I'm fully imagining like this alien species just coming and giving us like an equation, a crazy long equation, and then some scientists like spend years on it and are like, no way.
Yeah, because we have to like decode it, right? We have to decode it into our math and stuff.
Exactly.
But once we get it, it'll be crazy.
I think this is the funniest podcast we've recorded today.
So, okay, one thing I really wanted to talk about is the Planck length.
Oh, yeah.
Why is the Planck length so insane? Okay, for those who don't know, Planck length is basically the minimum distance anything can travel in our universe, right?
Well, no, technically it's the. Oh yeah, okay, sure, yeah. Anything can travel in the street,
right?
Yeah, sure.
So if you're standing still, perfectly still, you can be in one position, but as soon as you move, you have to go at least one Planck length. You cannot go half a Planck length or a quarter of a Planck length. You have to go one Planck length. How does this tie into simulation theory? This is crazy, okay? Think about your computer screen, man. Your computer screen has pixels, right? There's a minimum amount, there's a maximum amount of information you can put on your screen at once, because there are so many little lights that you can light up, and together you can string into images and things like that. It's the same idea when you turn it into 3 dimensions, right? If you think of a Planck length cubed, right? So it's a volume that has that, like a cube that has a side length of a Planck length. That is basically the minimum volume that you can occupy in the universe. So it's basically setting a resolution to the universe. So tying this back into the whole computer idea that the universe is in a computer simulation, there's only so much information you can store in the universe, because there is a limited amount of unit volume / length that you can occupy in this universe. Does that make sense?
Yeah, kind of. But how about this? Another way to put Planck length, or another kind of thing to think about, is, you know how we have the coldest temperature possible as minus 273, 0 Kelvin, or minus 273 degrees Celsius, right?
Yeah.
That's the coldest possible temperature. Now, on the other side of this is actually from a Vsauce video, by the way.
Wait, by the way, before you continue,
Yeah.
I just want to explain to the listeners why that is the coldest temperature possible. It's because when you are at 0 Kelvin, basically the atoms can't vibrate because it's so cold. So nothing can move, essentially. So that
basically at 0 Kelvin, they're like particles don't have any frequency. Like there's no. It takes away all the kinetic energy, I think. Yeah. Isn't that how they? Yeah, because that's how they're basically perfectly still.
Yeah, we didn't take
at 0 Kelvin.
We didn't take thermodynamics yet.
Not yet. Not yet.
Next semester.
Anyways, on the other side of it, we have the hottest temperature possible. What is the hottest temperature possible? Right? Now, this is where it gets interesting. The hottest temperature possible is basically, let's say any temperature exhibits a wavelength, right? It exhibits some radiation. That radiation has a wavelength. We can then measure that wavelength. So the hottest thing possible will radiate radiation at a wavelength of the Planck length. So the wavelength is so small. That's what basically.
Oh, that's crazy! So I never thought of that.
Exactly. So the wavelength is so small, right, that the length of the wave is equal to that of the Planck length.
That's actually pretty crazy.
Cool. So that's the other side. That's the hottest temperature possible. And that's also another interesting thing. Like, why is there a hottest temperature possible? Because of, again, this Planck length. But then that again poses why, right? Like, why can't we be smaller?
Yeah. Like, the problem with infinity when you're dealing with computers is that, if life wasn't a simulation, then infinity would be everywhere, right? There wouldn't be a maximum temperature. If you just heat something up infinitely, it would just keep going up and up and up, right? And there wouldn't be a minimum distance you can travel, because if I travel this far, I can just divide that by 2 and divide that by 2 all the way down. It's basically like a continuous region of space. But we're saying no, it's not continuous, it's quantized. There is a minimum amount of unit lengths you can travel. No, wait, not a minimum amount of unit length. There is a unit length that you can only travel, is what I'm trying to say.
So everything, basically, any unit length can be expressed in terms of Planck length, like in multiples, in integer, like greater than 1 multiples of the Planck length.
I wanted to talk about the last Thursday paradox.
Oh,
which is the actual name of the paradox.
Yeah, that's a pretty cool paradox. I know, I've heard about it.
So it's called, I'm pretty sure I mentioned this too on the last episode. We talked about something philosophical. Anyways, last Thursday paradox is basically, you cannot prove to yourself or to anyone else that the universe wasn't created last Thursday.
This is such an interesting paradox.
It's very stupid.
It's true. Right? There's no way. There's no way to answer it. Sorry, continue.
You can show me a video, right? Like, oh, this is a video from 2 years ago. This proves to me that the universe wasn't created last Thursday. But what if in the creation of the universe, right, your phone was created with already all of this information on it, in its storage, right? And all of your memories,
so stupid.
All of your memories were already encoded into your brain, and all of everybody else's memories were already encoded. And basically, back to that analogy of like a universe as a coding project, the alien that coded the universe already just put the information as is and pressed play, and then pressed play last Thursday, And now here we are. This is Friday today, so the next day, I can't prove to you that it wasn't created yesterday, because everything.
Interestingly enough, there's a group of people who believe in this, and the religion is called Last Thursdayism, and there's an actual church of Last Thursday, where people legitimately believe that the universe was created last Thursday.
Well.
And the interesting thing, as Parker just mentioned, is that there is no way for us to disprove that, because we can't measure the universe being created, and because in the universe's creation we are created with all of our memories, there's no way to tell if it was the universe that put in our memories or we that have had our memories.
Yeah, so the reason why this points to a simulated universe is because, well, I can't, like, to me, it's so obvious that the universe was not created last Thursday. But you know, is it?
But is it?
Is it? Did I just put on a VR headset in the fourth dimension and I spawned into this video game in my body last Thursday, and now I'm just chilling until the game's over, right? Like, there's no way for me to prove that.
There's no way.
So,
that's a pretty crazy paradox. Definitely read up on it if you want to hear a little more about Last Thursdayism and the religion. So yeah, I think it's pretty cool. But something I wanted to talk about real quick, even though we are talking about simulation now, if in fact, let's say our universe was or is a simulation, let's say we can somehow encode information to the universe, right? And now Parker was saying we describe negative infinity and infinity, but in reality, those things just don't exist. There is a minimum, there is a maximum. So we also know something about the maximum speed of something. What we know is the speed of light is a constant, and that is the fastest speed that anything can ever travel. And the only way to travel at that speed is to be massless. And we've already, I think, discussed this in some stuff before. But yeah, so that is the entire concept of the speed of light and how fast, quote unquote, it is, right? But if we suppose that the universe is a simulation, let's do a little thought experiment. Let's just think. What if the speed of light was crazy slow? What if it was like 300 kilometers an hour instead of 300,000 kilometers per second? Then what would actually happen, right? The universe would be very, very, very different. And we would technically not be able to move. Let me explain. So because of how energy is related to the speed of light with something known as the Lorenz Transformation. Don't want to go too deep into it, but basically what that states is as you get closer to the speed of light, the energy required to move further is very, very, very high. It's exponentially higher as you get closer and closer to the speed of light. Now, if the speed of light is 300 kilometers an hour, instead of 300,000 kilometers per second, if let's say you're on a highway traveling at like 150 kilometers or like 130 kilometers an hour, you would basically need, well, I don't even think we would have, there's no way we would have that technology, but we would need, okay, let's say we want to go 1 kilometer an hour. We would probably need 10 rocket engines just to propel our car 1 kilometer an hour. Because the speed of light is now so low. So every kilometer an hour closer to the speed of light, you're going to have to exponentially add more energy.
Yeah, that's crazy.
I think that's pretty cool.
To think about how, everyone knows E equals mc squared. And if the speed of light was very low, then what that indicates is that
E equals gamma mc squared. And the gamma is where this comes in play.
Yeah.
Because because the mc squared, if the speed of light was low, well, it really wouldn't tell us much about energy, right? It would just say energy is lower. But the gamma factor, that factor before the mc squared that many people forget to write, that is the most important factor. And that tells us it's the v squared over c squared factor. I don't know if people know that. That's awesome. So that basically is saying as you get closer to the speed of light, how much more energy would you need to add? And if it's slow, you would need to add a lot more energy. Also, time dilation would be a very big thing because the speed of light is so low. If you're traveling at highway speeds, let's say somehow you get to 150 kilometers an hour. Remember, forget the rocket, and let's say somehow you get at that speed. Basically, you would be dilating your time so much with respect to someone who is stationary and traveling, let's say, with Earth, right? That by the time you're done like a highway trip, you're going to be like 2 to 3 hours younger than someone who was just staying at home. And that's all because the speed of light would be so tiny, right?
Yeah, one thing I wanted to say is how you can visualize like a slow, how a slow speed of light would affect reality is that we know that the closer you get to the speed of light, the more energy you need. One way you can think of this is that the closer you get to the speed of light, the more mass you gain, right? And so the more kinetic energy you need to accelerate, right? Does that make sense?
Yeah.
Or let's say the faster you go, the more mass you gain, the more energy it takes to go faster.
Exactly.
And then that just keeps on adding up until you get to the speed of light, which you don't. You get very close to it, and then it becomes even harder to accelerate even more.
So that is exactly why we need to be, or someone or anything needs to be massless to travel at the speed of light, right? Because if you're not massless, then you just keep gaining mass till your mass reaches infinity at the speed of light. That's why it's impossible to reach that speed unless you're massless, right? But at the slower speed of light, things would be different. We would still not be able to reach it, but it would still take insanely amount of energy just to move like to 2 to 3 kilometers an hour, right?
Also, the final point I think we have is that the speed of light, why does that indicate that life is a simulation? Well, I wrote this down on the Google Doc. I said GTA analogy. I know everyone that played GTA. I don't know about GTA 5, but I used to play GTA 4 on PS3. And when you went really, really fast in just a straight line on the train tracks, basically the whole game would turn white. And this was due to the world not rendering like as you were riding through it. So the things behind you were getting rendered as you were already in front of them. So then your screen would just turn white, and then your character would be like riding on the motorcycle. And so that's kind of like the idea. There's a speed limit in the universe. So this is just kind of a cutoff to say that, well, if anything were to go faster than this, then it would be too strenuous on the computer to be able to render that much information at that speed for the observer, right?
And that's exactly what happens with light as well, because the faster you travel, also length contraction and everything takes into play. And I think we've spoken about this, right? Right?
My argument was also assuming that an observer can move faster than the speed of light.
Yeah, of course. No, but I'm just saying, like, because of, like, at the speed of light, like for a photon, let's say, for example, like the lengths are basically contracted so much that the universe doesn't even exist for a photon.
No, it's just a point. Like,
exactly.
Like
so
in the direction they travel, right?
Exactly. Nothing is defined for them because there's no length, there's no time, so a photon is basically just living its life. It doesn't know when it dies, when it's away. It just doesn't. Well, technically, it's not alive, but I'm just saying, trying to give a life to a photon, you know?
Yeah.
Okay.
But that we did talk about that before, but
yeah, I believe we have.
Yeah. So that's that pretty much concludes everything we wanted to talk about.
I think this was a pretty crazy podcast. We definitely had some good laughs, but I think more importantly, we got some points through that were really, really interesting. And, you know, just like points to think about. Obviously, if you ever want to search up simulation theory, that would also be really cool. You can just learn a lot from yourself. But I think we covered some good points today.
So, yeah, let us know if you enjoyed the episode today. You can always contact us on Instagram at math.physics.podcast or by email uoft.math.physics@gmail.com. Make sure to follow on Spotify or wherever you're listening, and leave a comment. If you have a question, we will always get back to you. Thank you for listening. So this has been episode number 32. I'm your host, Parker.
And I'm Ray, and we will see you soon.
Peace out.